We've already started? Okay. We'll start in 3, 2, 1. Good evening, everyone. It's February 5th, 2018, a cold night. And we're here to look at the wonderful topic of design force. I want to thank you all for being here. I want to thank Sean Maggio for being here to do the recording. Without him, we'd be stuck. So Sean, thank you. All right. My colleagues who are here in Kitty 228, I want this to be a worthwhile experience for you and for all of you at home or in the dorms, wherever you are watching this. I want this to be worthwhile. For on campus, don't hesitate to ask questions. If you have a question, I bet you someone in the home audience has a question. And Justine, they can't answer. They can't ask. They might be able to answer, but they can't ask. So if you have questions, feel free to ask. What I thought I'd do is go over last semester's exam. Now, if I've done it right, this should be posted on the course website. Okay? So what I'd like to do is to go over Quiz 1, Fall 2017. And what I've opened is the solutions. I had 2 versions, and from what I gather, I was able to put the solutions to both versions in this one document. So we'll look at as much as we can. I think there's a few interesting problems. Just a little note in the title, and I don't know if the title came out fully in Canvas. In the title, it says the last 2 equations on page 4 should be V out and not V thevenin. So when I get to page 4, if someone could remind me, the last 2 equations on page 4 should be V out and not VT. So I made an error and wanted to correct it. Okay, so E232, Quiz 1, Fall 2017. By the way, just one editorial comment. The exam covers chapters 2 and 3. At the time of this recording, we have not completed chapter 3 in the lecture. So this Friday, which is Friday the 9th, we'll be finishing chapter 3. So for those of you here tonight, you'll be seeing new material we haven't covered yet. All right? But the lecture is Friday. So the exam covers chapters 2 and 3. Okay? And we haven't yet covered all of it as of today in terms of the lecture. But let's take a look at things. So let's begin. And problem 1. Okay, let's just kind of read it together first before we look at the solution. And let's see if we can make sense of it. All right? So it says you're given a sensor which can be modeled as a first-order system. All right. All right. Okay, I think this is a chapter 2 problem. And the input to the sensor is a constant applied at t equals 0. And the constant input has a value of 25 for t greater than 0. So I'm just going to write down 25, t greater than 0. And the initial reading is minus 10. Okay? All right. Determine the maximum value of the time constant, tau, which will satisfy both of the following requirements. Now, why do I say maximum tau? See, if tau was very, very tiny, this system would respond very quickly. And usually, the smaller tau is, the more expensive the system is. So I want to pick the largest possible value of tau I can and still meet the system requirements. So I don't have to have an overly expensive system. So it says picks the maximum value of tau, which will satisfy the following 2 requirements. The time the sensor will take to reach 90% of its final value is no more than 1.7 seconds. That's one requirement. And the second requirement is the error is less than or equal to 16.15 at t equal 0.75. And the error is defined as the true value minus the output. It took me 5 minutes to read it. This problem is a killer, I think. I don't know. So I think, okay, wait a minute. Before I even get any further, what I'm hoping that you're comfortable with, and after all the time that we have done this, I suspect you're very good with this. This is the output of the sensor. Now, the input is 25. Now, since it's first order, I know it's going to get there. Now, where does it start? It starts at minus 10. That's the initial condition. So it starts at minus 10 and goes to 25 and asymptotically approaches 25. That's what this graph looks like. Now, what we got to do is solve this problem twice and get two answers for tau and pick the larger one. Or, let me put it this way, we need to pick the one that satisfies both. Okay, so maybe not the larger one. We need to pick the tau that satisfies both. Let me take that comment back about we picked the larger one. Okay, now, I'm hoping this makes sense. And if it doesn't, now, tonight is the time to stop me. We have a sensor. The input is x of t. The output is y of t. Since it's first order, I know the homogeneous is ke to the minus t over tau. And I know the final solution, the particular solution, equals the input. So I should be able to write down by inspection, the output is ke to the minus t over tau plus 25. Are we all good on that? Excellent. All right. So now, how do I solve for k? You know this. I solve for k using the initial condition. So I solve for k using the initial condition. So right here, I say at t equals 0, the value of y is minus 10. And Justine, I then put t into the exponent of e. So I get k times e to the 0 plus 25. Solving for k, k is minus 35. What I now get is this right here. Minus 35 e to the minus t over tau plus 25. Now, my colleagues, this is needed to solve the two parts of the problem. So this is it. If I lost you here, I'm going to lose you, and I don't want to do that. Are we all solid? All right. Now, we have to solve this twice, one for each requirement. So the first requirement is we need to determine tau such that 90% of the final value is achieved in less than or equal to 1.7 seconds. So I say, okay, what's 90% of the final value? 90% of the final value, oh, the final value is 25. So 90% of 25 gives me 22.5. I then say, great, I let that equal the output, 22.5. And now I solve this equation for tau. What do I put in for t? The 1.7 seconds. You see, it says less than or equal to 1.7 seconds. I'm going to pick equal to 1.7 seconds. That gives me the maximum time to get there, and tau won't be too small. So I'm going with 1.7 seconds, and I now solve this part of the equation for tau. Am I doing okay so far? So I now run down here and say, okay, how do I solve this for tau? It's all here, starting in the upper left-hand corner. And we take the natural log, and we get tau is 0.644 seconds. So the conclusion is, and I'll give you a moment to copy this, the maximum value of tau to satisfy the first requirement is 0.644 seconds. Okay. All right. Let me pause, make sure we're all good. Now, the second requirement, let's see what the value of tau we're going to get for that. Showing my colleague to help me understand the second requirement, I just want to go over here to the board and say, you know, what's the error, my colleagues? The error is the difference between the true value, which in this case is 25, and the actual value. And notice what happens. The error starts out, in this case, the largest here. And then it gets smaller over time, and as t approaches infinity, the error goes to 0. So that's what we're defining to be the error. So error, I say, good. The sensor error is 25. That's the true value, minus, this is the equation we derived. That's the measured value. So we got 25, which is the true value, minus the measured value. And I say, okay, remind me again, what are we required to achieve? That the error must be less than or equal to 16.15 at t equal 0.75 seconds. Okay. So what's happening here, my colleagues, and we can look over here. As tau, I want to make sure I say this right. I'm nervous because I'm on recording, and if I say something wrong, it will go viral. You know, our D4 professor, oh boy, look what he said. So I hope I say everything right here. The smaller I make tau, the quicker the system responds. Okay? So if tau was made smaller, we get up here quicker, and quicker yet, and quicker yet. Okay? Which is wonderful, but you're paying for that. So I want to pick the largest value of tau that satisfies that requirement. So the error must be 16.15 at 0.75 seconds. So again, I can plug in for t. So I'm just going to slide down so we can see the answer. Oh, by the way, I kind of glossed over something here. I didn't mean to. This is important. Forgive me. I didn't want to. Here. This equation here, this is the, as I was mentioning, the true value minus what we're reading. Notice 25 minus a minus 35, get that, but 25 minus, the 25s cancel out. Okay, so we're just left with positive because of the double negative. So Justine, we're left with positive 35 e to the minus t over tau. And that allows us then to say, okay, let's solve for tau. So it's now, again, taking natural logs. I suspect you're all very good at this. If you have any questions, let me know. So here I get a tau of 0.97 seconds. So I now have to think, and I'm bothered. I think I misspoke at the beginning. Here's how I now have to properly think. I've solved this problem twice. In one case, I got tau 0.644, and in the other case, tau is 0.97. Okay? Now, to satisfy both requirements, I picked the minimum value of tau. Right? And before I said maximum value, I apologize. Here we need to pick the smaller of the two. That's the largest I can have. One requirement says tau must be no bigger than 0.644. And the other requirement says tau can be no bigger than 0.97. To satisfy both, I got to use the 0.644. Did I say it right that time? We're all good? All right, thanks. That's problem one. I thought that was interesting. Have we done okay? My colleague, please. Got it. Let me, if I may, show me. I'll slide up. That's a good question. Hold on. Right. I need to go back up just one more line. So it's 90%. So 90% of the final value is 22.5. And then we divide, we subtract, pardon me, the 25. We got the minus 2.5. Did I? Good man. All right. That's problem one. We're all good? My colleagues, there's a version 1 problem here. Not every problem had a version 1 and a version 2. I think we just need to do one version. The other one is just different numbers. So that could be practice. Version 1. As I mentioned in lecture on Friday, this is like almost a guaranteed problem. This is something I really want to make sure you know how to solve. The point of this problem is you don't have to be an electrical engineer to design a filter. You could buy an op-amp and make it into a filter. So it's great. So if we look here, we have a low-pass Butterworth filter. Now, a very good colleague of mine sent me an email, and my colleague said, you know, it wasn't clear what was meant by nth order unity DC gain. So our colleague went online and did a search. I thought that was great. I didn't mean to confuse you on this. Let's see if we can figure it out. We're to design an nth order, unity DC gain. That means the gain at 0 hertz is unity, which is 1. Remember last Friday in class we spoke about active filters having a gain and being a filter? This is a filter, but it's not active because the gain is still 1. Okay? So a unity gain, unity DC gain, means that it's a gain of 1. Now, a low-pass Butterworth filter. I think it was the 1 o'clock section. We had a lot of fun with the name Butterworth. I think it was. We also had some fun in the 11 o'clock and the 3 o'clock. But we have a Butterworth filter. And it says that the sensor provides an output signal whose highest... Oh, it doesn't say what the highest frequency is. It says using a corner frequency of 20 hertz in the filter, determine the minimum order of the filter to satisfy the design requirement. And the design requirement is we need to significantly reduce this noise. Okay? So we have an output. I didn't tell you what the output was. I just told you what to make the corner frequency. So it turns out we want the voltage gain of the filter. I'm reading that bullet item. The voltage gain of the filter at the noise frequency, which is 60 hertz, should be less than or equal to minus 40 dB. So let me pause. I want to come over here to the board and tell you what some common mistakes are so you don't make them, okay? Here we're asking for the order of the filter to meet some requirement. It's a Butterworth filter. I'm hoping you know right away the formula to use. Now the formula is on the formula sheet, which by the way is at the end of this solution. But here's the formula. The gain at a frequency f is 1 over the square root of 1 plus f over fc, and then it's 2 times n, where n is the order of the filter. Now, you don't have to memorize this formula. It's on the formula sheet. So I say, okay, what's a number 1 common error? This gain to use for this formula must be non-dB. So this professor you got tries to trick you. He gives you the requirement in dB, thinking you're going to forget to change it. Okay? But you're not going to let that happen. Don't let that guy trick you. All right? So it says here, we'd like to have the gain to be less than or equal to minus 40. So the first 40 dB. So the first thing you got to do, and this formula is on the formula sheet also, is to convert minus 40 dB to a gain in non-dB. So it's minus 40 dB equals 20 times log to the base 10 of G, where G is the gain in non-dB. Okay. So we say, got it. You solve for that, and you get G is 0.01. That's the number you use here for non-dB, okay? 0.01 here, not the minus 40. Minus 40 will give you a crazy answer. So now, here's the formula, just as we wrote it on the board. And we say, okay, great. I now know what the gain at 60 hertz. Oh, here's the second place where people sometimes make a mistake. This F is the frequency at which you want to know the gain. In this case, that's 60 hertz. All right? So what we do here is we now plug into the formula, and let me slide up because the rest is plugging through. This is the key step right here. The gain at 60 is 1 over the square root of, now F 60, right? So it's 60. Make sure to put 60 here. And I tell you that the corner frequency is 20. Sometimes people flip these. Be careful. Don't. Okay, it's F over the corner frequency. And then the exponent is 2 times n. And what you put in for G, as we already mentioned, is the gain in non-dB, which is 0.01. You then go ahead and you solve for n. So there's a couple of ways of doing it. I like to use logs, but however you get it, you're going to find out that n is roughly 4.19. Now, here's the other place where colleagues make mistakes. They figure, oh, 4.19, that's close to 4, I'll pick 4. That's wrong. If you were to go back to that formula right up here, and if you were to put n equal 4, you would not satisfy the requirement that the gain is less than or equal to 0.01. N would have to be 4.19. Now, n is the order of the filter. It has to be an integer. So what do? Always go up. Even if it's 4.1, don't round it. It goes to 5. Okay, so it always goes up. That's the second problem. Let me pause. How are we doing? Okay, good.
For the yes, we're given, yeah?
I beg your pardon?
F and FC were given.
Yes. The question is, were F and FC given? Absolutely. I mentioned that the next to last line in the problem statement, the cutoff or corner frequency should be 20 hertz. And I mentioned I want to know the gain at 60 hertz. So you have to know that if I want the gain at that 60 hertz, that's F. Okay. Justine, I don't know if I see a question. I could be wrong. I think I see questions. No? Yes? Well, you can ask me anytime you want, Justine. Okay. All right. So that takes care of problem 2. Now, if I remember, there's a problem 2 version 3. My colleagues, it's the same thing. I think I just changed the gain and the cutoff frequency. There's no need to go through this. It would just be practice on your hand, on your part. So we can move on to problem 3. Oh, I virtually guaranteed on Friday that this was coming, and here it is. Okay, so let me all right. A sensor has a Thevenin equivalent circuit with a voltage V sub T. Oh, I think it was on this page. I might have made the typo. I used V out instead of VT. So my colleagues, page 4, yeah. So my colleagues, somewhere here I made a mistake. Let's see if we can correct it. So we have V Thevenin and the Thevenin resistance of 100 ohms. So my colleagues, I've had this question before. If I just throw out everything to the right, that's my model for a sensor. It's a Thevenin equivalent. Voltage source in series with the resistor, easy. Okay. Now suppose the output is too strong. It has too much voltage, and we need to connect this to some delicate measurement equipment. You know, very high accuracy. We don't want to have any damage. So we go through an attenuator. So the value of R1 is 1.5 K. The value of R2 is 5 K. Now, I mentioned that the output of the attenuator goes to a meter. Our author calls it a recorder. But think of it as a high precision meter. And we're going to measure something, the voltage. And it turns out the recorder or the meter has an input resistance Rn. Now notice, I don't show them connecting just yet. And you know why. You know I'm winding up to give you a loading error problem. And you know the loading error is V before minus V after. So notice I'm showing you the circuit before, and then I'm saying we're then going to connect it. So that's going to become the V after, okay? So it says here, determine the minimum input resistance so the loading error is less than or equal to 0.01 VT. So it's a little different than the lecture. In the lecture, I just asked you the loading error. Here, I'm giving you the loading error, and I'm saying how big does Rn have to be to make that loading error possible? So I'm asking it backwards. All right. So I say, okay, whether you ask it backwards or not, the loading error is before minus after. How are my two colleagues doing there? You're very thoughtful and you're looking good. You're making notes and everything. We're all set? We're good? All right. So we get loading error is before minus after. Is that it? Forgive me. Those are Eagles colors? Congratulations. All right. First time in since 1960, right? Way to go. Congratulations. I remember when the hockey team, the Rangers, won in '94. It had been since 1940. I remember my father and I were just unbelievable. A lot of joy in Philadelphia. Congratulations. All right. So now we're looking at the loading error is before minus the after. Now, I'm hoping the before is really easy. Before means before I connect to that meter. So this is voltage division, my colleagues. You can do this. I want the voltage across R2. So that's what I put in the numerator. And then I put in the denominator the other resistors that are in series, and I multiply by the total resistance, and I get 0.75 repeating times VT. Okay, so that's V out before. Now, what happens after? Come on, tell me. What are you going to do after we connect the two together? Help me out. Perfect. We're going to have an REQ because we're going to have two resistors in parallel. Thank you. All right. So I say, great. Let's now take a peek. Okay. Yeah, I see the typo. The last two equations, right? All right. We'll get there. We'll get there. I see my my error. Now after, so let me just go up here. After is, we now have an REQ, which is product over the sum. The unknown here is Rn. So I say, all right, that's unknown. So what I get is, this is REQ. And now using voltage division, what is V out? V out equals REQ divided by the sum of the resistors, which is the 100, the 1500 plus REQ. And we multiply it by the voltage source, V sub t. I now have an expression for V after. Now, I do a little algebra. I now substitute REQ into this equation in these two places. So I do a little algebra, I substitute in, and what I get is V out equals all of this times VT. How are we doing? It looks a mess, doesn't it? Can you believe I asked this? What was I thinking? I don't know. Okay. And what do we got to solve for? Don't tell me Rn. Yeah, we got to solve for Rn. How the heck are we going to do this? All right. So I think the next two lines is where I made the mistake. Just looking at the equation above, I have V out equals something times VT. I apologize. This should be V out, and this should be V out. Does that make sense? Okay. So each of those should be V out. And a little simplification. Okay, it's getting better. It's getting better. Okay. Now that's V out, and this is V out. So this is V out equals something times V Thevenin. And the loading error is before minus after. And I'm told what the loading error is to be. So the loading error is 0.75 VT, that was the before, minus the after. And I mentioned, I give you in the problem that we want this to be less than, in the last line of the problem statement, less than or equal to 0.01 VT. Now, just solve for Rn. Okay. So to determine the minimum input resistance, we have it there. The rest is just, it's not that bad. Okay. What I noticed, it was very sensitive to rounding. We have very large numbers and somewhat small numbers. So I made a note to the TA, you know, you could be off by 4,000 ohms if you just change a little bit of the numbers here. So roughly around 90, 91,000 should be Rn. How did we do? Silence. My colleague in the box seats, what do you think? How are we doing? We doing all right? All right. Okay. You now decide to perform a little experiment. I guess I decide to perform a little experiment, and I ask you to join me. That would be a fairer statement. And I say that I wonder how the loading error changes with resistor values. So you now select R1 to be 15K and R2 to be 50K. Using the value for the minimum input resistance in Part A, determine the loading error for the new values of R1 and R2. So let's just think for a moment. I know you're copying this. Forgive me for just a moment. Here. We had this here, right? What was the voltage divider? We had plus and minus VT, and then we went through a resistor here and one here. I wonder if anyone can help me out. If you can figure out, and then this is the connection to Rin. All right, does this make sense? This was 100K. Oh, excuse me, 100 ohms. And this was 1.5K. And this was 5K. And what was this value of Rin that we calculated? About 90,000? Around 90 or 91K. Is that correct? Okay. And that gave us a certain loading error, right? Okay. Now, that gave us a loading error of 0.01 VT. And it was like 91,000 to 94,000. Okay, now, help me out. I ask you to change the values. R1 is still 15K. But now R2 is 50K. You're making this 50K now. Okay? And the question is, using the same value of Rin, determine the loading error. The loading error going to go up or down? Let's see. Let's see. So the loading error before and after, we have before is V out as listed here, which is R2 over R Thevenin plus R1 plus R2 times VT. We get REQ, and then we get the V out after. Okay? Similar to what we had before. The loading error is before minus after. Now, plug in all the values. See, here we have the advantage of having the values. So we now plug in all the values, and the loading error is not what was it before, 0.01? Now it's roughly 0.08. Why is it larger? Help me out.
If you have a smaller resistor and a very large resistor, when they're in parallel, it's not, the resistance isn't going to change as much as
Right.
two larger resistors.
Right, exactly. So you have the concept of putting resistors in parallel. So why the loading error here is greater is for us to have a loading error of 0, we want no current to go this way. And if this is 5,000 ohms and this is roughly, let's say, 90,000 ohms, this is almost like a solid wall that no current goes. It's going to choose the 5K. However, as you now go from 5K to 50K, 90K is no longer the same multiple of 50K. So you don't get that solid wall. Current now more, or not evenly divides, but divides. So you're getting too much loading error. My colleagues, to have 0 loading error, before I connected this, I had current going through that resistor. Now I connect it, I don't want any current through this new resistor, none. And that's best achieved if that Rin that we're adding is many times the value of the resistor it is in parallel with. Did I say it right? Did I get your comment? Okay, great. All right. I thought that was an interesting experiment. I enjoyed it. Are we all good? So then I ask you what can you conclude about this? And this is exactly what you and I were discussing. I'll let you read this, my colleagues. It's in the notes here. But again, the larger Rin is compared to R2, or correspondingly, the smaller R2 is compared to Rin. the lower the loading error. In the part A, the ratio of the two was about 18. The loading error was 0.01. And then we had a ratio of about 1.8, significantly less. And the loading error was roughly 8 times that. We're up to number 4. Let me pause. How we doing in all of this? Doing all right? All right, so we have a 2-part problem. So you have a non-inverting 741 op amp with a DC voltage gain of 25 dB. And the input signal is given, and it says determine V out. Now, here's what you need to know. An op amp can change 2 things about the input signal: the amplitude and the phase. In our case, not the frequency. So the amplitude and the phase are going to change. So I say, okay, how do I figure this out? First thing I do, I get the gain in non-dB. I find it easier to get the gain in non-dB. So I have 25 dB equals 20 log to the base 10 of G. I solve for G, I get 17.78. I say, perfect. What is the peak input amplitude? 0.25 volts, right in front of the sign. So I then say, I take 0.25 and multiply it by 17.78, and I get 4.445 volts. That's the output. Now next, I need to know the phase change. Am I doing okay on this? I need to get the phase change. And I say, how do I get the phase change? Ah, yes, I remember in our exciting lecture on op amps, we said phase change is minus tan, or minus the arctan, pardon, minus tan to the minus 1, minus the arctan of F over F sub C. And I say, this is great. I can do this. And then, horror of horrors, I don't know F sub C. It's not given. F sub C is not given. Is there another way to find F sub C? Yes. I remember the joy of discovering the gain bandwidth product. I say, oh, what's the gain bandwidth product? Can I help? All right, let me pause. We're going to say, okay, help me out. What can I do to help you, or are you going to help me? Excellent. Question is, where did I get the peak output amplitude from? Okay, first of all, we're told in the problem that the gain is 25 dB. So I converted that to non-dB, and I got 17.78. So far, so good? Good. The next part is easy. You're going to get it right away. I need to just slide up to show you. I give you the input, and the input peak is 0.25, right at the top. So I just take 0.25 and multiply it by the gain, 17.78. And that then gives me the output peak voltage, in this case 4.45 we'll call it. Did I get it? Thank you. Thank you. All right, so I now say, I remember the gain bandwidth product. Now my colleagues, I don't think I have on the formula that the gain bandwidth product is a million. Okay? So just think of the op amp as a millionaire. Okay? So the op amp is a millionaire, and it has a gain bandwidth product of 1 million. So I now say the gain bandwidth product, I love the name, it tells me what it is. The gain times the corner frequency. And for the 741 op amp, that's a million. So I know the gain. How do I know the gain? I calculated it, 17.78. Another trick. Don't use dB in the gain bandwidth product formula. In the gain bandwidth product formula, the gain must be in non-dB. Okay? So then we say, excellent. I can now solve for the corner frequency, and I get a corner frequency a little over 56,000 hertz. I can then go back to the arctan formula minus the arctan. I put F over F sub C. F, where did I get F? Help me out. Exactly. Good man. It's perfect. It's 2 pi ft. Excellent job. Excellent job. 2 pi ft is the standard form. 2 pi ft. So F is 10,000. So the frequency is 10,000 hertz. And we just calculated the corner. And we calculate it. And we get an answer of minus 10.08 degrees. Remember, so far so good? All right. Please.
So now would we add this to the angle we were given?
I love what you just said. I love it because a very common mistake that people make is they say the output phase is minus 10.08. It's not. This formula, as you so accurately pointed out, phase change. Okay? So the output phase in this case is not minus 10.08. The phase change is minus 10.08. Now just to highlight that, what was the input phase angle? 14.5 degrees. Everyone see that? The input phase is 14.5 degrees. So now look at how I wrote it. That's the peak amplitude, which our colleague has already helped us with. And it's sine 2 pi f. F stays the same, 2 pi ft, plus, now it's 14.5 degrees, then minus 10.08. And we got it, and we're going good. How we doing? All right. Now, part B, you're given a first order unity DC gain. Okay, first order, N is 1. Unity DC gain, gain is 1. Okay, so you're given a first order unity DC gain of 1. Low pass Butterworth filter. Great. And the corner frequency is 750 hertz. The input signal is here. Determine V out. All right. Now, I think the first thing that I kind of notice here, the corner frequency of the filter okay. If I were to, draw in general what's happening here, if this is gain and this is frequency, it's constant and then it drops off, right? Now we're told, hello, I'm doing great, everything good? We're having a D4 review. Remember the good old days?
Oh, how could I forget?
Perfect. Perfect answer. It's good to see you both. Thanks for dropping in. Okay. F sub C is 750 hertz. Okay? So it starts to drop off. Now, at what's the frequency of our input? 3350. So I know I'm going to get less out because I'm somewhere, over here, 3350. I've already started to drop off. So I expect the answer, of course, to be smaller than what the input is here. So what formula do I use? Same formula we used earlier. Okay. Now, what do? I calculate the gain. Now, it doesn't surprise me the gain is less than 1. because I'm above the corner frequency. So the gain is less than 1. Makes perfect sense. Okay? So I say, all right, I plug in the F. Where did I get the F? I got the F from the input. F sub C, I was told that. And I was told it was first order. First order means N is 1. But I still get 2 here because it's 2 times N. God bless. And I get a gain of 0.218. Sean, help me out. Correct. Does this gain equation only work for Butterworth? Will I give you a non-Butterworth filter on the exam? No. Okay, because we didn't include the equations for Chebyshev and elliptic and Bessel. So Sean, we're going to stick with, as one of the sections told me, pancakes and toast. We're going to do the Butterworth filter. That's it. Okay, good. Thanks, Sean. Now, the next thing is we get the phase change, which is just what we did. We got F over F sub C. We know the input frequency. I told you the corner frequency. And as Sean pointed out, this again is a phase change of minus 77 degrees. So what we have is, and here I wrote it out. The input was 9.8 volts, but the gain is 0.218. That means the output is around 2.14 volts, less than what we put in, which is what we expected because the frequency is well above the corner frequency. We then have cosine 2 pi. Notice the F, just to emphasize this, the F stays the same. And then, again, going back to Sean's observation, which was excellent, it's, no, it wasn't, it was Vincent, right? Did I get your name wrong? No. Good, no, because I used to call you Anthony. A long time ago when I used to get all mixed up. And you gave me the look, and I said, I got all mixed up. I'm saying, oh, no. So, Vincent, we're good. I was like, Sean, I'm sorry. Vincent, I'm sorry. I'm just, I don't know what's happening other than it's after 10 o'clock at night. So, I'm sorry. I'll be right there.
The fact that it's cosine matter?
No. The fact that it cosine matter, no. We're not really using phasors here, so we're okay. I think you might be thinking back to the sine cosine. We're good. We're good, Vincent. Bella, help me out. Okay, good. See that? Great minds think alike. Okay, thank you both. Did I get it, Bella? Yeah. Okay, good. So that then becomes the answer. The frequency stays the same, and we get the phase angle here. All right, we're good? We're good. Okay, my colleagues, this is now for our studio audience, new material, okay? I'll go through it here. You might have questions, but on Friday, you're going to hear it again. And you might want to play this back in case you have a question. The op-amp can filter and it can amplify. Done. It can also integrate and differentiate. Okay? So it turns out that you are given a voltage signal which is given by V in equals T squared. Okay? And it's applied to an op-amp integrator. Now let me stop right there. I know we haven't discussed this, but this is the formula for the op-amp integrator. Don't memorize it. It's on the formula sheet. Okay? So when I tell you we have an op-amp integrator, this is V out. And over here is V in. And this here is the initial condition. So I say, okay, we're applying a signal whose input, the input signal is t squared for up to 5 seconds. It says determine the equation for the output voltage in 0 to 5 seconds. Okay. So what we need to do is to plug in t squared for V input. Everyone good with this? And I just plugged that in, and I also mentioned here that R times C equals 1. Fine, so this just becomes 1. And Justine, I mentioned that the initial condition is 0. So you have an integrator circuit. I tell you the input, and the input is t squared. So I just implement this by saying, oh, I know how to integrate that. That's t minus t cubed over 3. And from the mathematics point of view, this is valid from 0 to 5 seconds. Am I doing okay so far? Now, you're probably sitting there saying, there's a trick. This is too easy. There's a trick. And the trick is, you can't be more positive than 15 volts, and you can't be more negative than minus 15 volts at the output of the op amp. Why? Right. The input voltages that's powering it is plus and minus 15. So mathematically, this is the correct answer. But it can never go more negative than minus 15. So what we need to do is to say, when does this equal minus 15? So I just solved for that. At t equal 3.56 seconds, let's call it, or 557 seconds, that equals minus 15. Now, what happens when the output voltage gets to minus 15? It stays there. Doesn't get any bigger. Okay? So now we have the equation. We're done. How am I doing? So I say, good. How do we now get this? Look at this. Isn't this fancy? I think the math department would be proud of us. Okay? V out of t equals minus t cubed over 3. That's just the integral of the input. But when it gets to minus 15, it flattens out at minus 15. It stays there. It can't get any more negative. So the t then, from 0 to 3.557 seconds. Now, between 3.557 seconds and 5 seconds, because that's all the input lasts, we're stuck at minus 15. How do we do? That's an integrator. Not bad. You'll be aces on Friday during the lecture. Good. All right. Now, I forget if I added this in or not, but if there's an integrator, what else do you think we have? I don't know. I hope it's in this thing. Oh no, I go crazy on the comparator. Oh, I love this. Okay. No, wait, I don't want to show you this yet because you'll get panicky. I don't want you to get panicky. I want you to feel loved and the whole bit. So here. You can build something called a comparator with an op amp. And it's very, I don't have to know how to build. In fact, it's very simple. Here's how it works. This is our comparator. I'll just call it COMP. Is that okay? Now, this is the positive, and this is the negative, okay? Now, here's what happens, and then this is V out. My colleagues, if the positive input is a little bigger than the negative input, we get, let's say, positive epsilon. And what's the gain that the op amp is born with? 200,000. So epsilon times 200,000 is 15. So wait a minute. What have I just said? This is V positive. This is V negative. When V positive is greater than V negative, We then have a positive number going into this op amp. The gain of the op amp is 200,000. 200,000 times virtually any small number is 15. So V out, this is all you need, is 15. How am I doing? Now, who can take it the other way? My whole life passed in front of me. On YouTube. All right. All right. Help me out. V positive less than V negative. What happens here? You get a negative number, right? If V positive is less than V negative, V positive minus V negative is a negative number. A negative number times a huge gain, V out is minus 15. How am I doing? Mira, are we okay? Good. Bella, we're good? Ah, I had the same question. The chance of them being equal out to the umpteenth decimal place is 0. So we avoid that question. What actually happens is that's where it changes. If it was 15, it comes down to minus 15. If it was minus 15, that's when it shoots up to plus 15. So that's the area where it transitions. Did I do all right? Okay, now, all right, so I had to come up with a challenging way to ask this question. I don't know if you're going to appreciate this at this hour of the night, but here's the input. Okay, Justine, this is, I think. So now we need to be careful. See, I underlined this in the solution. The input voltage is applied to the negative input. The other version, I applied it to the positive. All right? So this is the input. Where do I apply the input? To the negative. Now, what's the positive voltage? 2. So the positive voltage is 2. And this is V in. Now, my colleagues, before we dive into it, if V in is less than 2, what's the output? If V in is less than 2, that means V positive is greater than V negative. The output's 15. What happens if V in is greater than 2? Then we get negative 15. So all you got to do, I know this looks crazy. It's not. All you got to do is find out when the input is below 2 and when it's above 2. That's it. So in the solution then, now, but just be careful. You know, I can put it to the negative or the positive, so you got to make sure to reason it out. The other version, I did it the opposite way, I think. All right? So here, I think I actually had fun doing this. I don't know. There, oh, I wrote it down. See that? Da-da-da, da-da-da-da. So if Vn is less than 2, it's positive, V 15. If Vn is greater than 2, output is negative at minus 15. So my colleagues, all you have to do, oh, that's version 2. All you have to do is to decide when am I below 2, right? So the first second, right? It takes me 2 seconds to get to 4 volts. In 1 second, I get to 2 volts, right? So at this point right here, I'm at 2 volts, and I stay there until 3 seconds. Okay? So in this interval, I'm bigger than 2 volts, and in the first 1 second, I'm less than 2 volts. So with that in mind, let's just jump down to the solution. Okay? So notice, when I'm less than 2 volts, the output is positive. That's the first second. And then from seconds 1, 2, up to 3, I'm greater than 2. So the output becomes minus 15. And you just keep going along. How did we do?
How do you know that's on 15 right at 1 and 3? How do you know it's exactly at 1 and 3?
Oh, how do I know it's exactly at 1 and 3? Because I hopefully drew it okay. I drew the function. So it reaches 4 at exactly 2 seconds. And it's a straight line as best I could draw it. So it reaches 2 at exactly 1 second. And then on the way down, it reaches 2 at exactly 3 seconds. Did I do okay? Bella, we're good?
Yeah.
We're good, everyone? Okay. Okay. You're going to be aces on Friday's lecture. Okay, we're up to 6. We're coming down the home stretch. By the way, my colleagues, you will not be in any way offending me if you have to leave. Sean and I, we're going to stay till the end. We have, I think, we have 3 more problems to go. If you have to leave, please don't stay here. You're great to stay with me this far. You can catch the rest on the video. So don't feel bad. Okay, a couple of short answer questions. I like this. It gets right to the point. Let's see how we do. A given sensor has both a systematic and a random error. Got it. The sensor has a range from minus 100 to 100 and an accuracy of 1% of full scale. Now, accuracy indicates random error. Okay? And it also has a systematic error of 1.5 volts. What's the maximum total possible error that you could have? So I say, okay, the systematic error is plus 1.5. Now, be careful. The accuracy is 1%. That's 0.01 times full scale, not 200. See, it goes from minus 100 to 100. You might think, oh, full scale is 200. No, no, no. Full scale is the maximum reading. God bless. So the full scale is 100. Okay? Full scale is 100. So we get plus or minus 1 for the random error. Now, to get maximum possible error, they both add together. So you get 1.5 plus 1. Maximum possible error is 2.5. Are we doing okay? All right. Now here comes all the fill in the blank questions. All right, here we go. What causes phase distortion? And it's, oh, excuse me. What property should an amplifier have to minimize phase distortion? I hope you know the phase angle must change linearly with frequency. So phase change is linear with frequency. We say, okay, I'm getting there. Next one, common mode rejection ratio. That's the ratio of the good gain to the bad gain. That's infinite. Okay. Oh. What is the rule of thumb for picking the resistors in an op amp? R1 and R2. 1,000 to 1,000,000. This came up in at least one of the lectures, I think all the lectures last Friday. A low-pass filter has a slope of minus 54 dB per octave. What's the order of the filter? The order of the filter goes down minus 6 dB as the order goes up. So it's minus 6, minus 12, minus 18, minus 24. Here, the filter is order 9. Aren't these short answer questions great? I love them. In and out, boom. It's like, you know, Jeopardy, design for $400. Ding! What is an active filter? I actually should give you the answer. You should write the question. That'd be good, like a Jeopardy. But I won't do that. I won't. What is an active filter? It's a gain bigger than 1. Now, we're up to number 7. Okay. We have only 2 more problems to go. Okay. Consider 3 amplifiers connected by cable. Now, the gain of amplifier 1 is G. The gain of amplifier 2 is 2G. As you can probably guess, the unknown is G. And the gain of amplifier number 3 is G. The total length of cable is 180 kilometers. L1 plus L2 is 180 kilometers. The cable has a loss, key word, has a loss of 0.4 dB per kilometer. V1 equals 3 volts. V out is 1.7. Determine G. I thought this was fun. All right? Now, what can help us out here is that everything is in dB. We're asked to find G in dB, the cable loss is in dB. So the first thing I do, now I want you to stop me here. I think this is an easy question, but I need you to help me out. V out over V in. Let's get that in dB. So that's 1.7 divided by 3 times log to the base 10 times 20. So I get a negative answer because V out is less than V in. And I get minus 4.9 dB. That means the total gain, which is really a loss, between V in and V out, the total gain is minus 4.933 dB. Now, everything else is in dB, and what do we do with dB? We add. So here we go. Minus 4.99 dB equals the gain of the first amplifier in dB, plus the gain of the second amplifier in dB, plus the gain of the third amplifier in dB. Now, minus the loss of the cable. How much cable do we have? 180 kilometers. What's the loss per cable? 0.4 dB per kilometer. We know everything except G. Solve for G, and you got it. So we solve for G, and that's it. Okay. All right. Good. All right. We're good? We're good. We're good, we're good, we're good. Last problem. You're coming down the home stretch. What do you think of this exam? Fair? Hard? Easy? Long.
I mean, like, circus was like, what, 3 problems?
Yeah, but circus, we only had 50 minutes.
Oh, that's right.
Here we have 100 minutes. So it should be at least double.
It's more than double.
Yeah, but that's because you're all smarter. You're, no, it's not the same. It's the same. It's the same credit. But you're smarter, so we have to prorate the credits to the smartness and credits. We have to. You know. You're right. It's not double the credits. This last problem, I must tell you, I liked it. It's easy. I had at least one person write a note on the exam about this problem, saying, "Oh, come on already." All right, you'll see what I mean. I thought it was fun, but my joy was not reciprocated. All right, so, okay, you'll see the pattern, okay? All right, I wanted you to think about the design of a low-pass filter. Okay. So, the input signal to this low-pass filter is 20 hertz. There's 100 hertz noise, also input. Okay. As you can guess, Sean, I want to get rid of the noise. All right, So we start out and say, okay, someone tells you the order of the filter is 2. Determine the value of the corner frequency such that the gain of the good signal is 0.99. Now, what's the good signal? The 20 hertz signal. So you want the gain of the good signal to be 0.99. Okay. Now, we plug everything. Oh, this formula, we now are so familiar with it. I want the gain at f equal to 20 hertz to be 0.99. So what I need to do is to calculate f sub c. Now, my colleagues, let me give you just a moment of background information, what I was thinking. This is what I was thinking, Sean, and I want to put it on the board here. Here. This is frequency, and this is gain. My colleagues, we're used to thinking of it like this. This is the Bode plot. And I remember in this room and in Bouchard and in other rooms pointing out that this is the break frequency or the corner frequency. Now what happens here? You are already down 3 dB. So that's 0.707. So if I had selected the corner frequency to be 20 hertz, the gain at the 20 hertz would be 0.707. So, Vincent, I don't want that. What I want is the gain at 20 hertz to be 0.9. That means that, somewhere, see, this starts to drop off, right? That means somewhere over here is 20 hertz. And the corner frequency has to be bigger than 20. I thought this was interesting. Okay? And we want to pick the corner frequency where the gain at 20 hertz is 0.99. So I say, okay, we just plug everything in. The gain is 0.99, 1 plus 20 over f sub c. And since it's second order, it's 2 times 2 is raised to the 4th. And my colleagues, look at this. Wow, I was like, this is interesting. The cutoff frequency is 53 hertz. Now, here's the problem. Where's the bad signal? 60 hertz. Was it 100? Was it 100? Okay, I'm sorry. We're getting close to 100 hertz. So now I ask what I thought was a great question. Determine the gain of the noise signal. So I say f is 100. Now I know the corner frequency is right around 53 hertz. So the gain of the good signal is 0.99. That's good. I like that. The gain of the bad signal is 0.27. I don't like that. It means I still got 27% of the bad signal. So what do? I love it. We increase the order because then it's going to drop off quicker, right? Okay. All right. So I say, ooh, this looks interesting. So what do? I was like, this is like a design problem, okay? You're told that 0.27, the gain of the bad signal is too much. You increase the order of the low-pass filter, and you let n equal 3. Now, what do? Repeat the same problem. We don't even have to go put n equal 3 in. Okay? Put n equal 3. You want the gain to be 0.99. Oh, look, since it drops off quicker, the corner doesn't have to be 60 anymore. We can move the corner closer to the 20 hertz. because it drops off steeper. It's like you're driving along and then there's a cliff. Okay? So I'm like, oh, this is great. Now, what question do I then ask? Exactly. What's the gain of the noise? It should be less because it's dropping off quicker. So I say, all right. 5.6% of the noise is left down from 27%. Now, this is where the colleagues revolted. Okay? There was moaning and gnashing, one comment being written after class, that was a little too much, Professor. I went for n equal 3. I know, I was crazy. I did the problem a third time. See, but I like this, you know, but that's okay. So I don't even have to show. It's the same thing. It's the same thing. Just let n equal 3. But I said, look at this. Now the corner goes to 32. Oh, the noise is 1%. I'm like, wow, this is interesting. You're down to 1% noise, 0.99 gain, and the corner is close to 20 hertz. I love this stuff. This is how you design a filter. Now, what did I get? Did I get any? No. No love, no. It was quite the opposite. I was like, rah, rah, rah. But they were good-natured about it. And then I ask you to explain it. Here's the formula sheet. Okay, it's all there. You have done the marathon. What time? I know we were a little late in starting. We started around 9:15, 9:20. Let the record show it's 20 minutes to 11. Wow. Sean, you the cameraman. You the cameraman. Thank you. Home audience, hope you enjoyed it. Hey, listen, I got 275 colleagues. In circuits, I think I got like 7 likes. I'd like to do a little better. Maybe just give me a thumbs up, you know, just every now and then, that's all. Just there's a like button. Yeah, I would like it. Then I can show my kids. Oh, yeah, I got downloaded 400 times. Good. How many likes? 2. All right, Dad, get out of here. All right. Good night, everybody. You're the best. What happened to reality?